Like I was saying, I did a lot of this work with Randall McDermott and Jason Floyd. So I started NIST about 3 years ago with a postdoc and came in and joined these guys in development for a lot of the combustion stuff for FDS6. Those two guys did a lot of the heavy lifting on some of the infrastructure, and I came in and worked with some of the combustion routines to try to help and clean things up specifically for CO. So I was very interested in CO. That's what my proposal was to get to NIST, and so hopefully you guys will be happy with some of the results. And so essentially what I'm going to talk about is a partially stirred batch reactor model, but really this is a talk on some of the new stuff in combustion in FDS6, and then some of the validation work we're doing with carbon monoxide predictions in under-ventilated fires. And so I'm going to give a brief motivation, and then there's kind of three things I'm going to talk about in terms of FDS6. And so one is the lump species approach, and so that's kind of our how we kind of change the way we interact with our users in terms of what they're allowed to do in terms of input files and combustion and chemical reactions and species. And then a little bit about the subgrid mixing environment, which is kind of what dictates how our combustion routine works, and then some of the chemical rate laws in terms of the two different types of reactions we typically use in FDS6, and then some validation results. And being that this is a fire talk, I do have fire videos, so we'll finally get to see some while we're here. So the first thing is motivation, right? It's like, why do we do this work? Why do we, continue to develop, and what are the needs? And so one of the things is CO. And so over the course of my 9 years, I guess, of doing fire research, I've worked a lot with the fire service. And so anytime, we deal with real fires, we worry about CO. So, the fire scene is an ideal H, right? That is immediately dangerous to life and health. And so that's both affecting firefighters and people. And so anytime we look at CO, we look at, what does that do to the person? And so one of the things I've worked with that I'm not going to talk about necessarily here is this picture on the right, which is contours of fractional effective dose, which is essentially, the likelihood a person might pass out when exposed to toxic gases. Here specifically, we looked at CO, CO2, and O2 deprivation. And we looked at different crew sizes and how they might respond to a high-rise fire. And so the more orange, the worse things are. And so one of the things we did in this simulation was we used a constant CO yield. So that's typical to what most people do in terms of FDS modeling. And so while that's not necessarily the best in terms of predicting the actual yields when these fires go under-ventilated, one of the things that, in terms of that analysis was looking at, assuming that it's constant, we can at least compare against the different crew sizes to show the different impact, right? We weren't necessarily caring with the actual values because it was a model case, but just that there were significant differences between the different crew sizes. And so that was kind of just a piece of it, but it's kind of led me to do a lot more work in terms of understanding CO and CO mechanisms. And so the first thing here, this equation that you see is, that's the LES species transport equation. And so the focus here is going to be on that last term in red, the m dot triple prime alpha. That's the mean chemical source term. And so how do we close that mean chemical source term when dealing with combustion? So I'm going to talk about three different things. The first is the generalized lump species, and then the next two are the batch reactor model. So that's kind of how we're handling the combustion. And then the fast and Arrhenius chemistry. Those are our two different rate laws when dealing with the types of reactions that you guys would typically find for an FDS simulation. And so first is our lump species via simple chemistry. So that equation up there, that's how we define. If you read the user's guide or technical reference guide, it's our simple chemistry. It's fuel plus air goes to product, right? That's how we know that's typically combustion. And so one of the things that we've allowed now in FDS6 is that fuel, that CmHNOANB, right? That can be defined on the input file. There is no longer a default fuel. I know that might upset some people, but now every time you run an FDS simulation with combustion, you have to define a fuel. And so whatever that fuel might be, at least now you know exactly what it is. I don't even know anymore what the default fuel in FDS 553. I think it was methane, propane. So I know you got a smile from Kevin about taking that default property out. And so the nice thing, though, is that Jason did a lot of work in terms of handling how we can, if you specify a fuel on the input file, right, whatever that fuel might be, if it's in that form, we will balance the chemical reaction. We assume it goes to those products there. And so that's the simple chemistry. It goes to CO, CO2, H2O, N2 and soot. And so you can specify a CO yield or a soot yield on the input file, and that will drive the right-hand side in terms of the concentrations of soot and CO. Now, sometimes that's not always the case. We don't always want to have just those species on the right-hand side, or we don't necessarily want to have a default yield. And so what we've also allowed users to do is now specify their own chemical reactions. And so you can specify any number of chemical reactions. I think we've tested it out to 19, 20 reactions, but I think Jason's recently made some updates that it goes a lot farther than that in terms of the number of reactions. I don't think there is a limit. I think there's just a limit on the number of primitive species we can handle. Is that correct? No, not anymore. So now I encourage you to try as most complicated as you can, and then if it doesn't work, please post to the issue tracker, and I will have to fix it. But then, oh, right, sorry. So yes, download the current source and do it, because the current release might break. But this is kind of a big thing for us, right? Because now you're allowed, if you wanted to have a PVC reaction and go to HCl and all their species, you can define this stuff on the input file. And so we give you the option to run in all primitive species or in lump species. And so a lump species is really, like you see here, a combination of species that will transport together, diffuse together, and react together. And the nice thing about that is when you can lump species, it's very advantageous in the code, because the less species we have to transport, the faster the code runs. So each primitive species nominally adds about 5%, give or take, to computation time. So this allows us to maintain speed while also giving you guys a lot of options. And so these are all things that are available, and they're very detailed explanations, both the user's guide and technical reference guide. So I highly encourage you guys to check those documents out, read them, ask questions, and we'll be happy to help in terms of helping you guys figure these things out. The one other thing, though, is when you start to deviate from the simple chemistry, when you define your own reactions, FDS does have a tight tolerance on atom balance. So you will have to be rigorous in terms of your chemical equation balancing to make sure that everything is proper, because we will not let you run a simulation if you're going to magically create or destroy atoms. So that we do have some physical laws that we have to follow. And so the first thing, that we started to focus on was mixing, right? So with FDS, what we do is we split the time integration in terms of the chemical species. So first we allow the species to mix, and then second we allow them to react. So this image up here is still from the video that you saw earlier. And so if you think of that red cell as a grid cell in FDS, right? So what we see there in that middle square is kind of an ideal, a true sense of what's going on in a computational cell. So everything in black there and everything in white there is kind of the unmixed state. And anything in gray is mixed. So we're going to mix towards the mean. And so the way we consider this is that differential equation down there, and it's a simple exponential decay. And what it says that over time, you're eventually everything is going to go from unmixed to mixed. This pretty much follows the interaction by exchange with mean mixing model. And so this top equation here is really just, that's telling you what the composition is in the cell. And so everything on the left-hand side, that delta, or the zeta of t, y tilde 0 of alpha, is everything in the unmixed state. And on the right-hand side, everything is in the mixed state. So it's a combination at any given time of the mixed and unmixed state in the cell. And only things that have entered the mixed state can react. And so that's kind of important. So based on the turbulence in the cell and the conditions that you have, unless you've mixed from the unmixed to mixed state, you cannot react. And so that's kind of driven all by that tau. And so that tau mix is based on the turbulence in the cell, and that'll drive the rate of mixing within the cell to allow for combustion. And so now once we've mixed and we've got something in the mixed state, the big thing is we have to solve that ordinary differential equation with the underline there, dy hat alpha dt. And so I realize that there's a lot of superscripts and subscripts and tildes and carets, and it's kind of very difficult to go through all of that nomenclature in a 20-minute talk, so I highly encourage you to read the technical reference guide. But essentially that dy alpha dt is kind of our rate. It's the change of species alpha with respect to time. And so the thing is, we do this two different ways. We do this in infinitely fast chemistry or finite rate chemistry. And so the nice thing is that we spent a lot of time here with writing an integrator to handle seamlessly the infinitely fast chemistry and the finite rate chemistry. And so with the finite rate chemistry, we have a fourth order integrator with error control and variable time stepping. Essentially, this means that you can dial in the error tolerance that you're willing to accept as far as your integration for the finite rate chemistry. And we've written an algorithm such that we're going to take the maximum allowable step such that you maintain your error tolerance. And then that step is dynamic. So as the chemistry becomes stiffer and the rates become faster, your time step will shrink. As the rates slow down, your time step will approach the time step of FDS. So we're trying not to have anything static or limiting in terms of how fast we can process your chemistry. And so for the most, I would say probably 95% of our applications of FDS, we use the mixed is burnt approximation. Essentially this means is once everything enters the mixed state in the cell, we allow things to burn based on the limiting reactant. So whether it's you're limited by fuel or the stoichiometric combination of oxygen, we will say whatever's mixed in that state, whether it's the limiting fuel or oxygen, will react. And so that drives how much fuel you consumed, right? You've either consumed all the fuel or the amount of fuel that you have oxygen to burn. And then we're able to, from that M.F, compute all the other species combinations. So if you change the fuel, based on the stoichiometric values of the chemical reaction that you've defined on your input file, we can then calculate all the changes in every other species that's involved in the reaction. And then from that, so then we generate this M.alpha. So that's just an array of change in species. And from the enthalpy of formations of each one of those species, that's how we compute your heat release rate. And so you can imagine that in any given cell, you have some unmixed species. They get mixed based on turbulence. Then based on the stoichiometry of your chemical reaction, they will react. You'll consume some fuel. That'll result in a change in all the remaining species. And then based on those properties of those species, there's your heat release rate. So that's kind of a very quick and dirty explanation of kind of how a lot of the combustion will work for 95% of the cases that people are using. But I wanted to go a little more in depth on something different, which is the chemical kinetics. So this is your finite rate chemistry. And so you can see there that dy hat f dt. So that's a little more complicated in terms of how we're processing that. So that's just an Arrhenius rate law. But you can imagine that if you've got several species all consuming different fuels, oxidizers, and all the different Arrhenius parameters, that becomes a very hard set of ODEs to solve. And so that's why we wrote that integrator, so that we can efficiently handle that reaction. But the other thing is we wanted to look more in depth in how do we predict CO. So this kind of goes into what I was talking about earlier, is we want to predict CO for under-ventilated fires. And so here's 3 reactions that we've kind of been using as far as our CO predictions are concerned. And so the first one is just a methane oxidation reaction, but instead of going to complete combustion to CO2 and H2O, we send it all to CO and H2O. And so this kind of follows the Westbrook and Dreyer mechanism from 1981. So it's a 2-step reaction with your primary fuel being oxidized to CO and H2O, and your CO-CO2 mechanism being a reversible reaction pair. So that's steps 2 and 3. And so one of the things we realized was that with finite rate chemistry and FDS on typical grid sizes, having a finite rate on your first step is kind of a challenge. It typically leads to having to use an igniter or really fine resolutions in order to get that finite rate chemistry to really go or start. So what we found was that using a fast chemistry step on that first reaction, that's the mixed is burned approach. And then as far as balancing out the CO-CO2 relationship, we use finite rate chemistry. And as far as the Arrhenius parameters are concerned, we started with Westbrook and Dreyer, and then we found this paper by Anderson et al. In 2009. And they did a lot of work as well based on using CFD and Westbrook and Dreyer's mechanism, and came up with a whole new set of Arrhenius parameters. And so we started with their Arrhenius parameters, but then we recalled this statement from Westbrook and Dreyer from their paper and said, that these parameters really are estimates, and they get you kind of close, but they might not be exactly right for your application. And so what we did was we started with Anderson's values and then looked at a small scale case and modified our parameters such that we could match what we were seeing in terms of the appropriate values for fuel, oxygen, CO, and temperature in terms of some of these results. So this here is a Wolfhard-Parker burner, so it's a small scale, several millimeter burner. And what we did was we started with we used the reaction mechanism that I showed on the previous slide in terms of all those Arrhenius parameters and all the other necessary things, and then looked at the results here. And so what I'm presenting here is on the left-hand side, that left column is fuel, the middle column is temperature, and the third column is CO concentration. And each row represents a different height above the burner. So the bottom row is 7 millimeters, the next row is 9 millimeters, and the top row is 11 millimeters. And so you can see we do a really good job of both the CO and the fuel concentrations. Our temperature profile is a little shifted, and I know it's going to be hard to see in that image, but in the Wolfhard-Parker burner, there's actually these big screens that sit over the burner. They're about 14 to 17 millimeters above the flame, and they're there to stabilize the flame. And so we have some feeling that that might have an issue with the shift, as well as the fact that this is really a 3D case that we simplified for a 2D case in terms of our simulations. So we're still not exactly sure why that shift occurs, but this was kind of what these are our results from kind of that mechanism for this case. And so the thing is anytime we do a simulation, we want to look at, if we're going to say this is the mechanism we're using, we want to look at different scales. And so the first scale was, like I said, that was about a 10 millimeter domain with 0.5 millimeter to 1/4 millimeter resolution. And we did it in 2D and in DNS as opposed to our typical LES simulations. And so here we went to a next larger scale. So these were experiments performed in 1994 by Nelson Briner and company. They were done at NIST, and they were on a reduced scale compartment. So this compartment is now on about a meter cubed. So we've got an order of magnitude from fractions of millimeters to a meter cubed. Our grid resolution is about 10 centimeters here, I believe. But we do have a bunch of grid resolutions that I'm going to present next. But I do have a simulation. And so one of the nice things of working at NIST is we get to work with Glenn Forney, and he does a lot of cool stuff in SmokeView. If this video will play. Oh, I guess I can't play it from my side. Oh, all right, well, we might not have that video. But let me say it's really cool. And so the nice thing, so that's using like the 3D volume rendering for looking at heat release rate. So what we do is we look at soot concentration and a 3D slice of temperature, and then Glenn does some magic, and we get realistic production from SmokeView. The one thing that I want to point out is in that back corner, you can kind of see where the flame is stopped, and we're kind of all, looks a lot like black smoke. That's kind of things that they were observing in the experiments, that we were starting to go under-ventilated in that back corner. There was not enough oxygen to really sustain combustion, and you were just getting some fire along that interface. So here are some results, since the video wasn't working. So what we did was we looked at CO concentration in the front of the rear of the compartment, as well as temperature. In our validation guide, we have a lot more things that we present, but for time, I'm only going to look at these two. And we looked at 3 different grid resolutions. So as y'all are familiar with the D-star over DX, we ran a 5, 10, and 20, so we have our kind of medium, coarse, and fine resolutions. And you can see that we have good CO predictions of CO concentrations and temperatures in the compartment, and that even for the 3 grid resolutions, we're doing a pretty good job in terms of predicting CO at a wide range of heat release rates. I think we go from 50 to 600 in terms of fire sizes in that compartment. And so the next thing was to go to a large scale situation. So now we went to a full scale experiments. These were also conducted at NIST. These were done in over 2007 to 2008. And so now this is, now we've gone from 1 meter to about 5 meters in size in terms of total volume, I think. And then the nice thing here is that the previous experiments were done with essentially natural gas or methane. Here we've got a wide range of fuels to really test this mechanism out, right? So we keep the same CO2 finite rate mechanism, but now we've changed fuels on that first side. So for all the different fuels, we still say, that fuel plus oxygen goes to CO and H2O, and then allow the CO2 CO finite rate mechanism to drive the CO concentrations in terms of what we're seeing. And so as I promised, hopefully this will work. So we do have a fire video.
It's fluctuating all the time.
We've got CO concentration in the bottom right here, and then the top 2 are just the standard heat release rate visualization from OPS. And you can see in that bottom left that we are going under-ventilated in that compartment. We're just going to the door and along the bottom. So this is pool fires. And these were pool fires. Obviously, we're starting to get a lot of less combustion. And you saw from the start of the video, it comes out from the natural burning. We definitely starting to start fast. So you can see that we've got a lot more CO concentration in the rear compartment. As far as now, let's look at some results. So the first thing we did was looked at the heptane results. So this is kind of a more common fuel that you'll typically see. On the top left, we have heat release rate. On the bottom left, we have temperature, and then we have CO concentrations in the front, the rear and front of the compartment. And so you see the temperatures on the bottom left. We have the temperatures are modeled fairly well. Our heat release rate, I'm not exactly sure why we have that initial dip. I know we've been working on trying to clean up some of the experiments. Kevin's done a lot of work there, and so I believe this is one of the cases where some of the input file needed some improvement over time, and so I think we might have some issues there. But we've run some more recently and shown some better results for the heptane. But as far as the CO is concerned, I mean, we don't exactly have the entire profile, but in terms of an engineering scale prediction for a fairly coarse resolution for predicting CO. This is an actual CO prediction. We're not specifying a yield as we typically would. And so we're definitely within kind of the ballpark in terms of both when we're peaking and overall CO concentration. So the next is to go to a little more complicated fuel. And so we looked at isopropanol. And so again, you can see the same setup for heat release rate, temperature, and CO concentrations. Our CO concentration is not as good here in the isopropanol. But the one thing that I wanted to point out here is that we are capturing those trends. So when things are spiking, we're spiking. When they're dropping. So we are getting the right profiles. There's still some work and some development work in terms of really capturing the true concentrations. And Kevin's done a lot of work recently with looking at a set of fast chemistry reactions for some of this as opposed to using the finite rate. But that wasn't yet ready for presenting, so we're still kind of in development in terms of some of that stuff. And the next is toluene, and so another more complex fuel. We see the heat release rate and temperature, we do really well. And here, as far as outside of a slight phase shift, our CO concentrations, both the front and rear of the compartment, are really well. And so some of this phase shift is due to time shrink factor that I was using so that we could get these simulations completed a little faster than normal. And so other than that, I was very pleased with the CO predictions here. Then as far as conclusions go, we've kind of overhauled the combustion from 553. We've got a lot more versatility for the user in terms of allowing them to generate their own reactions, specify them, both fast chemistry and finite rate, combinations thereof. We allow endothermic reactions as well, so that's your reverse reactions. We have fairly good predictions for CO concentration, which was a lot of the goal of this work. One of the things we want to do is look at transporting that zeta term, that unmixed fraction. So right now what we do is at every start of every time step, we assume zeta is unmixed and allow it to mix based on the turbulence. But we realize that it's not, once it's mixed, it's not going to unmix. And so that means we have to transport zeta. And zeta is a non-conserved passive scalar, so it doesn't impact the flow field. So it is something we could transport, but we don't really have the mechanism in place. That's something that Randy and I are going to be working on sometime soon, hopefully, in order to be able to transport zeta. One of the other things I wanted to add is something that I know some of you in the audience might be curious about is, you said we have multiple fast reactions, kind of set your own mechanism. But right now, extinction support is not currently there for multiple reactions. So with multiple fast reactions, you will have to set suppression equals false, but it is something we're working on. And then we want to continue to explore CO mechanisms. And so I just want to thank the National Research Council for kind of supporting my postdoc, which is what a lot of this work was done. The Nuclear Regulatory Commission for supporting a lot of the FDS development work. Everyone on the FDS development team. And then for some of the stuff we did with our mixing environment, Sean Smith from the University of Utah helped out a lot as well. And so with that, thank you guys very much.
Thank you. So a couple of questions from the audience. Anyone? No? Jason?
think this is just a comment on the alcohol thing. I remember back when I first started playing with this, came across one paper that said for the oxygen-containing fuels, you'll have some of the carbon will directly pyrolyze into CO at high temperature, which we don't capture in our model. So I think that's probably a big factor what's behind the discrepancy. We're not capturing that additional production that you might see.
Right. I figured, we are kind of limited in the way that mechanism is set up, that, we're saying fuel goes directly to CO and H2O, and, that's part of the limitations of the mechanism. Now, if someone had that mechanism to handle that in place, I think we certainly could do that kind of stuff. As far as looking at the rest of the species that we looked at in those experiments, the alcohols were definitely the most problematic in terms of our predictions.
Okay, no other questions. Thank you very much, Craig.